Hi everyone, so this is going to be the first set of notes for unit number 2. So we're starting unit 2, atomic theory, today. So if you're keeping your notebook and having different tabs for each unit, you want to go ahead and create your first one. So go ahead and put your name on your notes and we'll get started. So today's note sheet has a combination of notes and practice kind of mixed in. So there will be parts where I'm going to tell you to pause this video, do some of the practice, and then press play to check over your work. So as we begin, okay, atomic theory is basically the theory of atoms. So what is an atom? Okay, so all matter is made up of atoms. So that would mean the air, your desk, you, your cheeseburger, everything in this world is made up of atoms. And atoms are the building blocks of matter, the way that bricks are building blocks of houses, or that the cell is the building block of living things, okay? Now, atoms can be defined as the smallest particle of an element that maintains the identity. Okay, so it maintains the identity of the element. Okay, it's the smallest piece. Okay, for example, if you have a piece of gold, you can cut it up into smaller and smaller and smaller and smaller pieces, but once you get down to a single element, that's as small as you can get it, and it still be gold. Now, all atoms share the same properties. So one atom of gold is the same properties or things as another atom of gold. But gold and oxygen would be different elements, so they would have different properties. Now, there have been various models over the years of the atom. And so a model is just a simplified version of a very complex thing. Okay, and so we've had different models, and as we've learned more information through experimentation, we have adjusted our model. So the first model we're going to learn about was in 1803, and it was by this guy named Dalton, and he had the billiard ball model. That's what he called it. Now, billiard balls or billiards is like if you want to go play a game of pool, it's the balls that you play with, or if you're playing 8-ball on your phone, that's what we're talking about. Now, the thing is that he proposed that it was indivisible, meaning that this atom is completely solid. There are no other pieces that make it up, okay? And this is kind of what he said. Now, about 100 years later, okay, this guy, J.J. Thomson, came around and he had what he called the plum pudding model. Now, plum pudding is not something that most of us eat, so I like to think of it as the chocolate chip cookie model, okay? And so where you have your cookie, which has a positive charge, and then you have these negative electrons that are just sprinkled in, okay? And those would be the chocolate chips, okay? And so he discovered the electrons. That's what we call those negative charges. And he said these electrons just exist inside, excuse me, pardon the yawn in the middle of a video, that the negative charge just kind of exists and is randomly in this positive charge. And then a few years later, we get Ernest Rutherford, and he did an experiment called the gold foil experiment. It's very famous, okay? Sorry if you could hear the bell there. This is the gold foil experiment, and he discovered the nucleus. So at the center of the atom, there's a nucleus, which has a positive charge. And then we still have these electrons that are around that Thomson had discovered, okay? But the key thing here is that he discovered that it is that the atom is not solid. It's mostly empty space, because this is kind of what his experiment looked like. So there are these things called alpha particles, okay? And we're going to symbolize the alpha particles as this. It's the Greek letter alpha. Now, alpha particles are like radiation, so like alpha, beta, gamma radiation, things like that. And so what he did was he had a piece of gold foil, okay? So think of aluminum foil, but made up of gold. And he put it in the center of this ring, okay? And this ring was an alpha detector because alpha radiation is invisible. You can't see it. But what he did was he shot through a little hole in the detector, he shot these alpha particles. And what he expected is because up until that point, if that's gold, gold is solid. And so he said, okay, the alpha particles should hit the gold foil and then they should bounce back. Just like if I ran at a wall, I would bounce off of it like a cartoon. But much to his surprise, when he shot the alpha particles there, most of them went straight through. And every once in a while, it would hit something and be repelled, okay? And it would deflect depending on the angle. And so one thing to know about alpha particles is that they have a positive charge. And so what happens was when they would hit something that was positively charged, it would deflect because positive and positive repel each other. And so this is how he discovered that there at the very center was a positive, very dense area, and that the rest was mostly empty space. And so then eventually there was this guy, his name was Chadwick, which he doesn't get a lot of love. He's not on our list here, but he discovered the neutrons, okay? And these neutrons are located in the nucleus, okay? And then Niels Bohr came around and he proposed how electrons are arranged. So he said that there are fixed circular orbits around the nucleus. So if you have your center nucleus, he said that electrons are kind of like existing in rings around the nucleus. He said that's kind of like what it is. The key thing here being that it's fixed. So electrons stay on that energy level, and that is where they stay. Now, this is not actually true. Now, the Bohr model is what we use in class a lot because it's the easiest to draw. It's the easiest one to draw that is also the most accurate. But the most accurate of our models so far is called the electron cloud model. It's also called the quantum mechanical model. If you actually study chemistry, you'll take a class called quantum chemistry, and it's kind of like a calculus, physics, and chemistry class all in one. But it was developed by Schrödinger and Heisenberg. If you've ever heard of Schrödinger's cat, you know, the idea that you can't know where the cat is and how fast it's moving all at the same time, you know, kind of is it there or is it not there? And so in this electron cloud model, the idea is that the electrons occupy regions of space that we call orbitals around the nucleus, and it's determined by their energies and also by their probability. Okay, so the reason why we don't really draw this model in class is because let's say this center part is our nucleus. Okay, every time I put a dot, that is a chance that you could find an electron. Now notice, close to the nucleus, there are lots of dots because the closer you are to the nucleus, the more likely you are to find an electron. But as you move further away, the dots are a little more spread out, okay? That's because you have less and less of a chance of finding an electron in that spot. And so I can even draw one way out here. That's why when we draw atoms as having a boundary around them, okay, like just a circle, that's not actually true, okay? It's not like an electron is going to hit a wall and then be like, oh, can't go further, okay? There are no defined boundaries in an atom. Okay, there's the nucleus and then your electrons all around it. Now, that's our most updated model. And they changed over time as we did experiments and our technology increased. Okay, now in these atoms, okay, we have the subatomic particles that were discovered. And so an atom has three parts. You have your proton, which is positively charged and is the symbol P with a plus sign as a exponent. The neutron, which is neutral or zero charge, So it's N with a 0 as the exponent. And an electron is negatively charged, which is an E with a minus sign. Okay. Now, the proton and neutron are found in the center of the atom, which is called the nucleus. Okay, and that's what Rutherford discovered. And so the electrons are going to orbit the nucleus. Okay, now they don't orbit completely the way planets do around the sun, but they do move around a lot around the nucleus. So, our particles, we have the proton, we have the neutron, and we have the electron. Okay, now proton and neutron are located in the nucleus, okay, which is at the very center, whereas the electrons are in orbitals. Okay, sometimes you'll see it referred to as the electron cloud because it's just like surrounding it. Now, when we look at the charge, okay, is the atom positive or negative? Is the particle positive or negative? Protons have a positive 1 charge, electrons have a negative 1 charge, and neutrons have a charge of 0 or neutral. Now, the mass. There's an acronym, AMU, not an acronym, a symbol. Well, I guess it is an acronym, and it stands for Atomic Mass Unit. Okay, so with the atomic mass unit, it tells you how much it weighs. So a proton weighs 1 AMU. Okay, a neutron also weighs 1 AMU. It technically weighs a little more than that, but we kind of round it to make our math easier. And an electron weighs 0 AMU. Now, an electron doesn't actually weigh 0 amount. However, it takes about 1,800, give or take a little, electrons to weigh the same as 1 proton. Okay, so if you take away or add an electron, it basically does nothing to the mass because it's so tiny. Okay, so on the next page, we're going to kind of go through our periodic table, which the periodic table is linked on eClass. Okay, and if you want a physical version of the periodic table and you don't have one, I've got laminated copies for every single student. Just come see me in class. But your periodic table is going to be used on quizzes, on tests, on assignments, and you have to use the periodic table that I give you. If you're at home, you cannot just like Google periodic table and find what comes up, because the numbers that are right here kind of change from periodic table to periodic table depending on how they round them. So when you're looking at your periodic table, the number that's at the top, that's your atomic number, okay? And your atomic number tells you the number of protons in an atom or the number of electrons, but it only tells you the electrons if the atom is neutral, okay? If it's not neutral, then there's different things that you have to take into consideration, like the charge and things like that. But most of the time, our atoms are neutral unless I tell you otherwise. Then we have our symbol, the element name, and we have the average atomic mass. Now, there are different atoms of oxygen that have different mass numbers, okay? Because our mass number is equal to our protons plus our neutrons. And you can't have half or 0.99 of a proton. You either have a proton or you don't have a proton. You either have a neutron or you don't have a neutron. But because there are different types, we end up taking an average, and so an average is why you end up having these decimals. So your mass number, okay, is going to be your average mass rounded to a whole number, okay? So it's your average mass rounded. Okay, we want a whole number for that. So if we look at an example, for example, lithium. So if we look at Li, the missing part in the box is the name. So I write lithium because I'm using my periodic table. And I see that my atomic number is 3. Now remember, if this is neutral, and I want you to assume that all are neutral, that they're all neutral atoms, then that means that the atomic number is 3, and so are the protons and the electrons. Okay, so that's how we get those two. Now, the atomic mass is 6.941. However, for our mass number, we want to round to a whole number, so that would make it 7. And so our neutrons, remember neutrons, your mass is your protons plus your neutrons. So that means neutrons would be your mass number minus your protons, which would give you 4. So what I want you to do is I want you to pause the video and I want you to complete the rest of these, okay? And I will go through a couple of them when you press play. Okay, so hopefully you've completed some of them. So I'm going to go through bromine. So bromine on the periodic table has a symbol of a capital B and a lowercase r. Make sure when you're doing this that you're actually paying attention to capital versus lowercase, because capital C, lowercase o, and capital C, capital O are very different things. So capital C, lowercase o is the element cobalt on the periodic table. But if you have a capital C and a capital O, that means you're talking about carbon and oxygen. So you have two different elements there, whereas cobalt would just be one element. So your uppercase and lowercase letters matter. So the atomic number for bromine is 35, because that's the number at the top. The atomic mass is 80. The number of protons is 35. The number of neutrons would be 80 minus 35, so you get 45. And then the number of electrons is also 35, because we assume that it's a neutral atom, so the protons and electrons must be the same. Okay, so if you want, if you're not sure about some of these other ones, you can send me a message on Remind, and I can check your work. Okay, now for this one here, you should be able to complete this by using the missing pieces as clue, or the pieces that are given to you as a clue, and your periodic table to be able to fill in the missing part. Now, one thing that you need to be able to do is you need to assume that the atoms are neutral. Okay, otherwise you won't be able to complete it. So assume that they're neutral. And then you should be able to fill in the missing blanks and things like that, the symbols and all of that here. So again, you can pause the video and complete your practice and then press play when you're ready to go. Okay, so you should have already completed this practice and have it filled in. One thing, I'll go through a couple of them. So argon has the symbol of A, capital A, lowercase r. The atomic number is 18. And because the atomic number is 18, and this is a neutral atom, I know that the protons are 18, and because it's neutral, I must also have 18 electrons. Now, the mass number, according to the periodic table, is 39.95, so rounded to a whole number is 40. And so to get our neutrons, it would be 40 minus 18. Okay, so 40 minus 18, which gives me 22 neutrons. Okay, so we can do another one. For example, this one. Okay, it's got 53 electrons. Well, that means if this atom is neutral, it must also have 53 protons and have an atomic number of 53. And if you look on the periodic table, number 53 is iodine, which has the symbol of a capital I. Okay, and the atomic mass is 127. And so 127 minus 53 would give you 74 neutrons. So you should be able to fill in the whole chart. Now for your blanks, you should know that the atomic number tells you the number of protons that are in one atom of the element. It also tells you the number of electrons if the atom is neutral. So they're talking about a neutral atom. And how the protons or atomic number gives the identity of the element as well as its location on the periodic table. Periodic table is arranged by those numbers, okay? Read it like a book, starting at the top and go from left to right. Now, no two different elements will have the same number of protons. If it has 8 protons, it has to be oxygen every single time. If it had 9 protons, it would no longer be oxygen. It would be fluorine, which is number 9 on the periodic table. Now, when you're looking at this, naming the element with the following number of particles. If I have 26 electrons and 29 neutrons and 26 protons, the identity, okay, or the name is based only on the protons and nothing else. So if I have 26 protons, that means that we're talking about the element iron, okay? If I have 0 neutrons, now this one is tricky, okay? This one is tricky because remember, your neutrons are your mass number minus the protons, okay? And so what you need to look at is if you look at hydrogen, hydrogen has a mass of 1 and 1 proton. So when you subtract the two, you get 0. So 0 neutrons is we're talking about hydrogen. It is the only one that does not have neutrons in its atom. Well, most of them don't. Some do, but most do not have any neutrons. So you should be able to use your protons. And then antimony, guys, antimony is Sb. And so if you have the number of electrons, that should be 51 electrons, okay? So you can use that. Uranium is a U, and it's number 92, so it has 92 electrons, okay? So you should be able to fill in all of that. Now, Bohr diagrams. This is the last part of the actual notes, and I'll give you an example, and then you need to do the rest on your own. So Bohr's diagrams, named after Niels Bohr, who we learned about at the beginning of the video, are simplified models that show how the electrons are arranged. Okay, it shows how the electrons are arranged surrounding the nucleus of the atom. Okay, so what you do is you find your element, you determine the number of electrons, it's the same as the atomic number, and then that's how many electrons you will draw. Now, remember that electrons are organized into orbitals or energy levels. Okay, now on your periodic table has this general shape. Okay, which this is not a great periodic table. And there are rows, okay? Each of the rows are called a period, okay? It's why it's called the periodic table. So rows are side to side or horizontal. So you have 1, 2, 3, 4, 5, 6, 7. And then these two at the bottom are part of row 6 and 7. There's like a little spot here. It says star, and then there's stars. And that means that that's where those elements go. You'll notice a break in the numbers there. And so each row is also an energy level, okay? So that means on row 1, notice that there's hydrogen and there's helium. They're just 2 elements. And that gives you a hint that on level 1, it can only hold 2 electrons. Now, level 2 and level 3, if you count, can hold up to 8, okay? And you have to fill in the lowest level first before you can move to the next level. And this is a really important vocabulary word here, valence electrons. So valence electrons are electrons located in the atom's highest energy level that's actually used. So the highest level for electrons. Now, when we look at this, now your paper might be in a different order than mine, but you should have all 4 of these elements. So I'm going to look at magnesium first. Magnesium is Mg on the periodic table, and it is number 12 and has a mass number of 24. Because its atomic number is 12, that means I have 12 protons and 12 electrons. Again, assume that these are all neutral atoms, and that our neutrons, 24 minus 12, is also 12. Now, a Bohr model has the protons and neutrons at the center. So I'm going to draw 12 protons, 12 neutrons, and then I'm going to draw my levels as rings around the nucleus. Okay, now those are not perfect rings, but they're there. Now, for electrons, I'm going to draw each electron as this green dot. And because we have to fill in the lowest energy level first, remember this energy level closest to the nucleus, that's level number 1. Level number 1 can only hold 2 electrons. I have 12. So I'm going to put 2 of them there, and I put them on opposite sides of each other because electrons are negative and they repel each other, so they don't want to be close. Now I have 10 more electrons I need to put on there. Level 2 can hold 8 of those, so I'm going to put them there, and I'm going to separate them. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 on level 2, 2 on level 1, 10 total. I need 2 more, so I'm going to put 1 and 2. Now, because these atoms here that I just put on are on the highest energy level that magnesium has, okay, that means that I have 2 valence electrons. Now, an electron is an E with a negative sign, so a valence electron just has a V in front of it. And you should be able to use this to draw the models for your other atoms. So you can check your work with me if you need to, and you may go ahead and get started completing your practice.